In this example, we're assuming we've got a hockey puck sliding along a frictionless surface, and we're talking about a top-down view here. So let's assume this is north, south, east, west. So this direction doesn't mean up on the diagram. This direction means in the northwards direction. So we apply, or it's moving to the east, and its motion would be the direction of what vector? What quantity do we use to describe the direction it's moving, or its motion in general? We describe it as the positive x direction, but what quantity describes the motion of an object? Its momentum, or also its velocity would work. I would say that its velocity and its momentum are both pointing to the east direction. So we'd say it has a velocity to the east, and also it has a momentum to the east. So its velocity is how fast it's moving and what direction it's traveling in as a vector. So we might say its velocity is, let's say it's moving 10 meters per second. We would say its velocity is 10 meters per second to the east. And then its momentum is just that velocity times its mass. So let me throw in some numbers here just to, let me get some more light also. Let's throw in some numbers just to have some examples to work with, even though this problem didn't provide any numbers. But let's say it's moving at 10 meters per second. Then its velocity would be 10 meters per second to the east. So velocity has a speed and a direction, magnitude and direction. And we could also write that in terms of components. We could say 10, 0 meters per second. And then for its momentum, how do you convert velocity into momentum? Yeah, multiplied by mass. So let's say the mass is known. Let's say the mass is 4 kilograms. Then the momentum would just be 10 meters per second times 4 kilograms, including direction. So 10 meters per second times 4 kilograms would be 40 kilogram meters per second. And that would still be in the eastwards direction, the positive x direction, because multiplying by a scalar, multiplying by a positive scalar doesn't change the direction. If we had multiplied by a negative scalar, that would just flip it to the exact opposite direction. So we would describe that as 40, 0 kilogram meters per second. So these might be some examples. And of course, the mass, yes, mass is a scalar because it's just magnitude, it doesn't have direction. In general, if you're not sure whether a quantity counts as a vector or a scalar, ask yourself, does direction make a difference? Like for instance, traveling 10 meters per second to the east and 10 meters per second to the southwest or 10 meters per second up would be very different types of motion. Or a force, for instance. If you're pulling with a force of 3 newtons to the north, or if you're pulling with a force of the same newtons up, even if it's the same magnitude, different directions means it's a different quantity. But for mass, you wouldn't say an object has a mass of 4 kilograms to the south or 4 kilograms downwards. It's just 4 kilograms. So for mass, direction doesn't matter. Direction doesn't even make sense attached to mass. Likewise, you wouldn't say if something has a temperature of 500 kelvins to the northeast. It's just 500 kelvins. So if attaching a direction to the quantity doesn't really make any sense, then that means that quantity is a scalar. It's just a magnitude. Of course, scalars can be positive or negative. That's almost like a direction, but not really in the same way. Whereas a vector quantity is something where direction actually matters. Direction makes a difference. Any other questions on that so far? And of course, these are just examples of possible values. The problem itself didn't actually provide any numbers. What the problem is saying is we're assuming the object is moving to the east and it experiences a kick pointing to the north. So if we were to draw out a free body diagram for that, the object is experiencing a force to the north. And it's what we might call an instantaneous force. It's a strong force for a very short amount of time, an instantaneous kick. So we're not really applying a force for a long period of time. We're just hitting it and then not touching it again. What does a force do to the object? What does a force cause to happen? You apply a force to an object, what happens to it? Yeah, a force causes a change in momentum. That's really what force is. Force causes change in momentum. Specifically, we would say the total force acting on an object. The sum of the forces on one object. In other words, the net force. This is what we mean by net force here. Net force is just the sum total of all the forces acting on the object. Changes momentum and possibly including direction. Yeah, and the thing is when we say changing the momentum, since momentum is a vector quantity, changing the momentum might mean the magnitude or might mean changing the direction or might mean changing both. Those would all be included as possibilities. So let's take a look at this idea of net force. The net force acting on an object can cause a change in momentum. And specifically, if we take a look at the units of measurement there, what are the usual units of measurement of force? What do we measure force in? Like if we said the strength of the force was 5, what are the units of measurement for force? 5 what? Yeah, 5 newtons. Force is measured in newtons. Anyone know what newtons is an abbreviation for? Like when we describe a force as 5 newtons, what does newtons actually mean? Joules per second. I think it's actually joules per meter. Joules per second would be watts, the unit of power. But yeah, we can write it as joule or kilogram meters per second squared. Kilogram meters per second squared. And the reason for this has to do with another equation that force shows up in. Sometimes it's useful, I mean, a force definitely causes a change in momentum. But a useful way to think about that, the changing momentum, momentum is mass times velocity. When you apply a force to change the momentum, are you changing the mass of the object or changing the velocity of the object? Yeah, presumably the mass is staying the same. We're causing a change in velocity. And what do you call the rate at which velocity changes? How would you describe, like if the velocity is changing, what do you call the rate of change in velocity? Speed is just the magnitude of velocity, how fast the object is going. But if the object is changing velocity, like let's say it's getting faster and faster, yeah, that's acceleration. Force causes acceleration to happen. And acceleration counts as a vector because acceleration is the rate of change in velocity. Acceleration is just describing how fast velocity is changing as time passes. So if velocity is a vector, that means acceleration is also a vector. And as you said, velocity is measured in meters per second. Divide by seconds again, because time is measured in seconds. So meters per second for velocity divided by seconds for time. And we get meters per second squared. Because the seconds in the denominator and another seconds in the denominator combine together. So acceleration is measured in meters per second squared. But the units don't quite match up here. What else do we need here to get kilogram meters per second squared? Yeah, we're going to need mass. If you multiply mass times acceleration, the units work out. You get the units for force, kilogram meters per second squared. And this is, in fact, what a force does. A very useful way of thinking about forces is that the total force acting on an object causes acceleration to happen. And those should be proportional. More force means more acceleration. Like if you apply 3 times as much force, the object is going to accelerate 3 times as much. And mass is the constant of proportionality here. The more massive an object is, the more force is needed to make the object accelerate. In fact, a very useful way of thinking about mass in the context of motion is that mass is a difficulty level. Mass is a measure of how difficult it is to accelerate the object. If you want an object to accelerate at a certain rate, then it's going to take a certain amount of force to make that happen. The more massive the object is, the more force is needed. So let's say you want the same acceleration, but you have an object that's 3 times as massive, you're going to need 3 times as much force to make that same acceleration happen. Or to put it another way, if you apply the same force to an object that's 3 times as massive, you only get 1/3 as much acceleration. But there's always this proportionality going in. So I think it's very useful for anything involving motion, pretty much for the rest of anything involving the study of motion. It's useful to think of mass as a difficulty level. Mass is a description of how difficult it is to accelerate the object, how much effort it takes to change that velocity. Any other questions on that so far? And another very useful way to rearrange the equation here, if we replace acceleration with its definition, if we go back to the idea that acceleration is change in velocity over change in time, and instead of the derivative, I'm going to write this out as delta v over delta t. Formally, this should be the derivative of velocity, but we can approximate that as change in velocity over change in time, at least if we're talking about a short period of time. So in that case, we can rearrange these terms a little bit. If I combine the mass with the delta v, what do we call mass times change in velocity? Kinetic energy would be if the velocity was squared. Kinetic energy is half the mass times velocity squared. But yeah, this is all about momentum, right? Also known as impulse, yes. Because momentum is defined as mass times velocity. If we apply a delta to both sides, mass is constant, and any constant multiplier can be pulled out of the delta. So mass times delta velocity. So this m times delta v is the change in momentum, which is, yes, also called the impulse. Usually written as lowercase j as a vector. So impulse is change in momentum. And the reason why we use a different variable for that and instead of just calling it change in momentum is you might have several impulses acting on an object. Each one of those impulses is an attempt to change the momentum. The actual change in momentum is the total of all the impulses acting on the object. But if you actually write that out as change in momentum, we get what might sometimes be a much more useful idea of force. So the net force is equal to mass times acceleration. The net force is also equal to how fast the momentum is changing. So you can think of this as 2 different ways. I mean, it's really the same thing, just written in 2 different formats. You can think of force as causing acceleration with mass representing the difficulty level, or you could think of force as changing the momentum as time passes. And the amount of force is the derivative of momentum. In fact, this was apparently how Newton defined force in the first place. Force is being defined as the derivative of momentum, because he had just invented calculus and wanted to define everything as derivatives. So that's what force does to momentum. Force causes momentum to change as time passes. And we can even solve this for delta P. If you isolate delta P here, what do you get? Or how would you isolate change in momentum here? Yeah, multiplied force, specifically the net force, times how much time the force lasts. And the thing is, you can do this individually for, let's say there's several forces acting on the object. You can do this individually for each force. One single force acting on the object times how much time the force lasts, that force times that time causes at least some attempt to change the momentum. There might be several forces acting for various different amounts of time, but all of those force times time added up gives you the actual change in momentum. So this is what we call an impulse. An impulse just means a force applied for some amount of time. If you multiply force times time, that tells you the amount of delta momentum that force is trying to cause. And the actual change in momentum of the object is all of those individual impulses added together. Any questions on that so far? So let's go back to the hockey puck. We are applying a force to the object in the northwards direction. That force is, so presumably we've got a very strong force applied for a very short amount of time. We can multiply those, strong northward force times short amount of time, to get the impulse. So the impulse, the change in momentum is force times time. And if you take a northward force and multiply by time, which is a scalar, the direction is not going to change. We're going to get an upwards change in momentum. And now that we know the change in momentum, we can just add these together. We can say that the initial momentum plus the change is going to equal the final momentum. Final momentum equals initial momentum plus change in momentum. We know the initial momentum is purely in the eastwards direction. We're adding a delta momentum in the northwards direction. And we can do this as the head to tail geometric method. We've got a vector to the east, we're adding a vector to the north. So the actual result is going to be in this direction from head to tail. So that's the final momentum. In other words, the puck is now moving in the, let's say, the east-northeast direction. The kick is the force, but that force times the amount of time tells you the change in momentum. So yeah, generally I would say the kick itself is applying a force, but that force lasts for a certain amount of time. That force from the kick times how much time the kick lasts. And time here is basically the amount of time that the foot is in contact with the puck. And that's presumably just a tiny fraction of a second. So the amount of force provided by the kick times the amount of time the kick is in contact with the puck tells you the change in momentum as a result of that. And so the puck is now moving in this direction, let's say east-northeast, as its new final momentum. And final velocity will be in that direction also, because velocity is just momentum with mass divided out of it. And if it's now moving in this direction, what sort of path would you expect it to take? From this point onward, is it going to go in a curved path or a straight line? Is it going to get faster or slower? What would you expect? It should go in a straight line, right? Its new path is going to look like this. Because the only way it can change its momentum after this, exactly, we're assuming no friction, we're assuming the kick only lasts for an instant and no longer applies any force at all. With no more force, there's going to be no further change in momentum. The momentum stays this new value forever until another force acts on it. And that's one of the really important things to keep in mind about motion. We generally expect the momentum of an object to stay constant unless there's a force acting on it right now. If there's a force acting on it, that force changes the momentum. Yes, we would assume it's staying the same speed in the same direction, so a constant velocity, because the only thing that would change velocity is an external force. So if there's a force acting on it, that force might make it speed up or slow down or change direction to make a curved path. But if there's no external forces acting on it, or if there are external forces, but they all cancel out, then we assume that the momentum does not change. It keeps moving at the same speed in a straight line forever. In general, anytime you have an object that is getting faster or slower, or is changing its direction so it's following a curved path, then you know there must be some sort of force acting on it. If there is friction, friction would act as a force in the opposite direction of motion. So if there was friction, the force of friction would be acting in a direction opposite to the motion. In general, anytime you've got surfaces sliding on each other, friction is going to be a force acting opposite to the direction of the slide. So if there was friction, it would be in the direction opposite to momentum, and that would make it gradually get slower and slower, eventually coming to a stop. Any other questions on that so far? All right, let's try applying some of these same ideas or similar ideas to the idea of a collision and use get an introduction to this concept of the momentum chart. Let's say we have two objects that are, one moment, please. Speed will stay, yeah, as soon as friction begins, then the speed will start to decrease immediately. Because as soon as there is friction, as soon as you introduce a new force, that force immediately starts changing the momentum. Because force is the rate of change in momentum. If there's a force, then that means the momentum is changing as time passes. If it's a constant force, that means the momentum is changing at a steady rate. If the force is 0, that means there is no rate of change for momentum. Momentum stays constant. So let's take a look at an example where you've got a couple of objects colliding. We often just look at hypothetical examples of rocks colliding out in space. So let's say we've got two asteroids out in space colliding. Let's say we've got rock A with a mass of 100 kilograms traveling directly to the northeast. So a 45-degree angle with a speed of 20 meters per second. And let's say that's going to collide with rock B, whose mass is 300 kilograms, which is moving to the west at 10 meters per second. So let's say here's our initial system. And by the way, why would you expect that we see so many examples involving rocks colliding out in space? Sadly, it is not a NASA sponsorship. I don't actually get paid by NASA for this. That is true. We are a rock in space. Earth is a rock in space. It's a lot more than 100 kilograms. But yeah, a big part of this really is that we don't have to worry about gravity. We're assuming we're far from any planets or stars, so we can ignore gravity. We're assuming we're not in an atmosphere, so what other force can we ignore? Yeah, there's no friction with the air, no air resistance. And also, since the objects aren't resting on a surface, there's no friction and no normal force. Generally, if you've got an object like on the ground, if you just got, let's say, a block on the ground, gravity's pulling it down. Why is it not falling through the ground though? Yeah, the ground itself is applying an upward force. Gravity is pulling the object straight down, but the ground itself is applying a force preventing the object from going through the ground. Anytime you've got two objects in contact with each other and like trying to push through each other, these surfaces apply what we call a normal force. Yeah, it's one example of a contact force. In general, a contact force means any force that requires the objects to be physically touching each other in order to work. For example, gravity is not a contact force. You can have the Earth applying a force of gravity to an object, even if the object is not touching the ground. But what we have here is an example of a contact force. The ground is pushing up on the object. and we call that a normal force. Normal is just a fancy mathematical word for perpendicular. Perpendicular in the sense that the force itself is perpendicular to the surface. So in general, anytime you've got two objects in contact with each other, then the surfaces can be applying a normal force to each other to prevent the objects from passing through each other. And yes, gravity would be an example of a long-range force because it can act at any distance, even if the objects are not touching. Other examples of long-range forces would be electrical attraction and repulsion and magnetism. I think those are the only long-range forces we're going to be looking at in the 7 series. There are some other ones, but they only really matter at like subatomic levels anyway. All the other forces we're going to care about are contact forces. Like a tension force only applies if the rope is actually connected to the object. A spring force only applies if the object is actually touching the spring. Normal force only applies if the object is pushing on some other surface. Friction force only applies if two objects are in contact and sliding against each other. So all those other forces have to be contact forces. In this case, though, we're assuming that the objects are out in deep space, so we don't have to worry about all these other forces. We're assuming no gravity in any significant way. They're far away from planets. So there is still gravity, but it's very weak. No atmosphere, so we can ignore any force of air resistance. No surfaces they're resting on, so we don't have to worry about friction or normal forces. They're going to be applying forces to each other during the collision, but that's internal forces. That's influencing each other within the system, but it's nothing outside the system influencing the system. So what we can do here is we can assume that momentum is conserved. Because going back to the idea that the idea of impulse, that force times time, the force on an object times time causes a change in momentum for that object. But the thing is, even though these rocks are individual objects, we can treat the whole system as if it's one big object. So the change in momentum for the whole system, if we just treat the rocks together as one distributed object, the force we're going to be looking at is any external forces. We don't really care if we're talking about the change in momentum for the whole system, the change in total momentum. We don't really care about individual forces of rock A on rock B and rock B on rock A. We care about external forces. In the sense of forces from something else acting on rock A or B. So if there were other forces from elsewhere, like gravity or, I don't know, solar wind or cosmic radiation or something, or maybe a spaceship hitting one of them with a tractor beam, then there would be an external force, a force from somewhere else, and that would change the total momentum of the whole system. But if we assume they're only interacting with each other by colliding, then any forces will be internal forces, force of rock A acting on rock B, and force of rock B acting on rock A. Those change the individual momentum of each rock. Maybe rock A contributes some momentum to rock B, but they don't change the total momentum because one of the rocks is losing the same amount of momentum as the other one is gaining. The changes cancel each other out. So if there's no external force, then we know that total momentum is conserved. There's no change in total momentum. So we can say that if the sum of the external forces is 0, maybe there even are some external forces, but they add up to 0, then we know that the change in total momentum of the whole system is 0. And we write a vector sign over the 0 here because we're not really talking about the number 0. We're talking about a vector whose components are all 0, whose magnitude is 0. And another way you could say change in momentum is 0 is you could say that the initial total momentum is the same as the final total momentum. Same thing, just written a different way. And you could just write this all out as equations. This whole thing could be done entirely with equations without any diagrams at all. But this idea of a momentum chart is a very convenient way of organizing the information. And the main idea here is we're going to draw out a chart with columns representing initial value of momentum, change in momentum, and final value of momentum. And we're going to do this for each object in the system and also for total. So a column for initial, change, and final, and a row for each object in the system and total. So this is the general structure of what a momentum chart will look like. And you may have more than two objects. It's entirely possible to do this for more than two objects. In this case, though, there's only two objects colliding. And first thing you want to do, if possible, are there any external forces acting on these? With no external forces, what is the one cell here that we can immediately fill in?
The total impulse will be 0.
Yes, we've got 0 total impulse from outside. So that means the total change in momentum has to be 0. So we can fill that in immediately. We know that there is 0 change to the total momentum because there's no external forces. This is the whole idea of momentum being conserved. We know that the initial value total must match the final value total because there's no change. So this is something important to keep in mind. If there's no external forces at all, or if there are external forces but they add up to 0, then you know that the change in total momentum must be 0, which means whatever the initial value is has to be the same as whatever the final value is in terms of the total. With that out of the way, let's also try filling in whatever other values we can. We don't know anything about the final situation yet, but we do know something about the initial values. For instance, for rock B, what's the initial momentum?
The 10 times 300?
Yeah, 10 times 300, so that'll be 3,000 kilogram meters per second. And direction matters here because it's a vector, so 3,000 to the west. And these are all going to be in kilogram meters per second. I don't want to have to write that out every single time, so I'm just going to make a little note here that all of these values are in kilogram meters per second. And what about rock A? Yeah, 20 times 100 would be 2,000 kilogram meters per second, and that'll be to the northeast. And then for total, can I just add 2,000 and 3,000 to get 5,000? Does that work? Yeah, in this case, I can't do that. You can only just add 2,000. Are there any circumstances when you could just add the 2,000 and 3,000?
When they're moving in the same direction?
Yeah, if both of those momentum vectors were in the same direction, then you could just add the magnitudes together. But since they're not in the same direction, this is a two-dimensional problem, not a one-dimensional problem, we're going to have to write these in terms of their components. So if we split these out into components, rock B, I think, is going to be pretty straightforward because that's basically along one of the axes anyway. So how would you write rock B as its component?
0, negative 3,000.
Yeah. Or I list the 3,000 first.
Or sorry, negative 3,000, 0.
Yeah, so negative 3,000, comma 0. And then for A, we're going to need to use a bit of trigonometry. We've got 2,000 along this axis, along this hypotenuse. And we want to split it into the X and Y components. However, the 45-degree angle makes that a lot more straightforward because that means these are both 45. And how would we find these missing sides? If we call these, for instance, PAX, or sorry, PAY and PAX. We could use the Pythagorean theorem here. The fact that this is a 45, 45, 90 triangle tells us that these two sides are the same as each other. So we can say this squared plus itself squared is 2,000. So PAX squared plus another copy of it equals 2,000. And then divide both sides by 2 and take the square root. So we'll get 10 root 10. Which doesn't seem right. Oh, I forgot to square the 2,000. So 2 times PAX squared would be 4 million. Divide by 2, we get 2 million. And then take the square root, we get 1,000 times square root of 2. So you could use the Pythagorean theorem here because we know that these two sides are the same. But that's not always going to be true. That's only going to happen if it happens to be 45 degrees. More generally, how would you find the x component and y component? Yeah, I would use sine and cosine here in most cases. Yeah, because we know that cosine, for instance, let's switch the color here. Cosine of, let's say, this angle. Ignoring the other angle for now. And in general, if you have the option of using angles, I would just always use the angle that the vector makes with the positive x-axis. That vector, that angle is usually referred to as standard position and is generally the most straightforward to use just so we have some consistency. In that case, since cosine of the angle is talking about the adjacent side, if you're using the angle that the vector makes with the positive x-axis, then the x component will always be the adjacent side. So cosine of the angle is the x component over the magnitude. So that means the x component is going to be the magnitude times cosine of the angle. And then likewise, the y component will be the exact same thing, but using which trigonometric function instead?
Sine.
Yeah, we would just use sine instead, because sine is about the opposite side, and the y component is opposite from the standard angle. And in this case, sine and cosine of 45 degrees are both square root of 2 over 2. So we just get square root of 2 times half of 2,000, square root of 2 times 1,000, which is about 1,414. So that'll be both the x component and y component. And since this is to the east and north, those will both be positive. So 1,414, comma 1,414. And I'm rounding off a bit here, but that should be close enough. So we now have x and y components of both A's initial momentum and B's initial momentum. Any questions on that so far? And then we can just add those together. X component plus S component, negative 3,000 plus 1,414 would be 1,586, is that it? Yeah, that should work. And then 1,414 plus 0. So we now have the x and y components. And for the calculations, all we really need is the x, y components. But in terms of understanding what's going on, it's a good idea to draw out the vector as well. We've got 1,586 to the west and 1,414 to the north. So that'll look something like this. And notice that that's going to be the same amount north as this one, because the northwards component didn't change. But it's going to be a much shorter westward component because the westward component and the eastward component partly cancel out. And since we've got no total change, the final amount should be the same as the initial total. So this is also going to be that same negative 1,586, comma 1,414. Any questions on that so far? So if you have all the initial values of mass and velocity, you can calculate the initial momentum of each object, write that in x, y components using sine and cosine as needed, add those together one component at a time to get the initial total momentum. And if it is a closed system, if there's no external forces, then you know that the final total momentum is the same as that initial total momentum. Coming up next, we're going to need to find the final, or ideally we want to find the final values. The problem is there's too many unknowns here. We know that this value plus this value adds up to this known value, but we don't know how it splits up. Maybe we've got, maybe A is everything and B has come to a complete stop. Or maybe B's final momentum is the whole thing and A has come to a complete stop. Or maybe it's split up equally, or maybe one of them has a very large amount, the other one is in the opposite direction. There's infinitely many combinations of two vectors that would add up to this. So this alone is not enough information. We're going to need one more piece of information here. And that would typically be given in the problem. Maybe we are told what A is doing. Maybe we're told that B comes to a complete stop and we want to find what happens to A. Or maybe we're told that they bounce off of each other in opposite directions with the same speed. Or maybe we know which direction each one's going, but we don't know how fast they're going. We just need one more piece of information and that should be enough. Let's say in this case that our one more piece of information is that they stick together. That maybe these are made of some sort of soft rock and when they hit each other, they just sort of merge into one object. So let's assume that that's what the final situation looks like. So let's say the final situation is rocks A and B merged together into just one big rock. And we want to know what's that one big rock doing? Which direction is it moving? How fast is it traveling? And the one thing that tells us, if two objects are stuck together, what does that tell you about their final values?
Their final velocities are the same.
Exactly. We know they have to have the same final velocity. Not only the same magnitude, but even the same direction. In other words, we don't really even need to label V final A and V final B. It's just V final. There's one final velocity for the whole system. And so even though we don't know what these values are, we can write each one of those out as a mass times velocity. Mass A and mass B times V final A and V final B. But again, since we have the same final velocity, we don't need to label that with a subscript. It's not V final A and V final B, it's just V final. And we know what those masses are. So we can now write this out by saying this final momentum plus this final momentum equals this total momentum. Mass A times V final plus mass B times V final equals total momentum, which we know. And since it's the same V final, what can you do with this same V final algebraically if it's the same multiplier in each term? Yeah, you can factor that out. Factor out V final, we're left with just MA plus MB. In other words, we're taking the combined mass times the final velocity. This is essentially just treating it as one big object anyway. In the momentum chart, we're still treating it as two objects that happen to be traveling together because you don't want to change how many objects you're talking about halfway through the problem. So in terms of the chart, we're treating A and B as separate objects that just happen to be moving together. But mathematically, that still works out to combining the masses under one speed. And then how would you solve for V final here? Yeah, we divide both sides by that combined mass. V final is going to be total momentum divided by the combined mass. And let's try working that out. We know total momentum in terms of its components, because keep in mind, this is a vector. Total momentum is negative 1586, 1414. And in terms of units, that's still kilogram meters per second. And we're dividing by, what is the total mass here?
400.
Yeah, 400 kilograms. And that means, how would you divide a vector in terms of components by a scalar? How would you actually calculate that?
Would you divide each component separately?
Yeah, we can do this one component at a time. So we take negative 1586 divided by 400. And we get negative 3 points, and pretty close to negative 4. Let's round that off a bit. And then 1414 divided by 400 is about 3.5. Kilograms cancel out, so we're left with meters per second. So we now know the components, xy components of the final velocity. We could then multiply that by each mass individually to find the xy components of each individual momentum. So these values times 100, these values times 300. And that would tell us the individual momentum of each object in the system in the final situation. And from those, you could then even find the changes in momentum by just subtracting final minus initial to get delta, final minus initial to get delta. And of course, you'd want to do that one component at a time as well. And sometimes that's not really necessary. Sometimes maybe all we care about is what's the final velocity. So you have xy components. How would you convert that into magnitude and direction, by the way, if you wanted to know how fast it's actually moving? If we know its final velocity is 4 to the west and 3.5 to the north, how would you find the...
Wouldn't it be C is equal to the square root of a squared plus b squared?
Yeah, we could use Pythagorean theorem to find the final velocity. So that'll be square root of 4 squared plus 3.5 squared. And then how would you find the angle here? If we're trying to find, let's say, this angle.
Oh, you could use inverse tan.
Right, because tangent of that angle should be opposite over adjacent, and we have both of those. So say tangent of the angle equals 3.5 over 4. Let's say we ignore the signs here. 3.5 over 4, then take the inverse tangent, and that'll tell you the angle. And make sure your calculator is set to degree mode if you want degrees, or radian mode if you want radians. So that'll tell you how fast it's moving and in what direction. And maybe that's all we care about. But you can also fill in the change momentum column, which can be useful in several ways. First of all, it can be useful as one final check. Make sure the changes really do add up to 0. And they won't be exactly 0 here because we rounded it off, but they should be pretty close to 0. And also, the change in momentum can be useful for other reasons. What causes a change in momentum? Remember the idea of impulse we were looking at earlier?
Force times time?
Yeah, it should be equal to force times what? Yeah, force times time. So if you know the change in momentum of, let's say, rock A, that should be equal to the force that rock A experiences from rock B times the amount of time the collision lasted. So if you also know how much time the collision took, maybe you've got a video of this event and you can play it in slow motion and measure how much time it takes between first contact and settling into the new final situation. So if you know how much the change in momentum is from just subtracting final minus initial, and you know how much time the collision takes, you can divide by time and figure out exactly how much force was involved in that collision. Specifically, the force that rock B exerts on rock A to make rock A's momentum change. So that's another thing this change in momentum column can be useful for. It can be one final check to make sure everything fits together mathematically, and you can also use it to find information about the forces acting on one object from the other. And those should be equal and opposite forces. As A and B collide, A exerts a force on B in one direction, B exerts the exact same amount of force on A in the opposite direction. These are the equal and opposite forces that Newton's third law is talking about. Any other questions on that?
Casey, I have a clarifying question about the third column. So I know we solved for the -4 and 3.5, which could be multiplied with the MA and MB respectively. Mm-hmm. So then when we solved for the VF using the Pythagorean theorem, then what value, where would we use that VF?
That would be how fast the final combined rock is moving.
Okay, the combined.
So that might be, for instance, the final answer we're looking for. How fast is this rock moving? And also perhaps which direction is it moving in? And for that.
So would that, oh, sorry, go ahead. Go ahead.
For the direction, we would just use inverse tangent.
Okay.
So since we know the X and Y components, we can just take the inverse tangent of 3.5 over 4, and the inverse tangent would tell us this angle.
Okay, so then that hypotenuse, that VF could be used for the third row then, for the total final momentum, right?
For these?
Or no? The third row. The negative 1586, is that where it would go?
Oh, this?
I'm sorry, no, just for the last, for the total final momentum, could we then use the VF there?
We don't really need to, because we already have the X and Y components of the final momentum.
Okay.
If you wanted to know the magnitude, you could just take the, use the Pythagorean Theorem on these values.
Okay, thanks.
Mm-hmm. Any other questions on that? All right, try applying this to other examples, anything you've got on your homework or practice quizzes. And it's fairly straightforward to just make up your own examples as well if you want some more practice. Just make up some object with some mass, some other object with some other mass, make up some directions and speeds so they will collide, and also make up something about the final situation. Maybe say, assume they stick together, or maybe say, assume that one of them comes to a complete stop, or something like that. Feel free to make up whatever examples you want. And I would recommend, as you make up the example, try predicting just intuitively, what would you expect to be the realistic thing that would result? Then actually run the numbers and see what should happen, and compare that to your intuitive guess about what you think should happen. It's a good way to train your intuition to get better at predicting in advance what you would expect to happen. Any other questions on that? You're welcome. See you next time.
Thank you.